Hello! In this video, I'll be diving deeper into CAD and off-the-shelf part integration into your custom builds using Fusion 360. I normally use SolidWorks since that is what I'm certified in, but I also use Fusion for a lot of other projects, like the Red Cat Rampage XB gas to electric conversion video that's on my channel. Recently, I got a stadium truck body for my 3D printed RC build, but it was from the early 2000s, being a Team Losi Triple XT body, so the window masking was oxidized and no longer sticky, but I was able to scan and load the negative into Fusion, trace the lines, and export a DXF so I could laser cut some masking to use. If you don't currently have Fusion 360, I have a link in the description of where to go to get the free version. Once you load up Fusion, it can be a little overwhelming and intimidating if you've never used CAD before, or are used to easy CAD softwares like SketchUp and Tinkercad. For this video, we'll be staying in the design workspace. If you want to know more about the other workspaces or any selection for that matter, just mouse over it. For the sake of time, I will be only going over the design tools that I use as I use them for the video. If you're like me, you learn well by doing, so after watching, you can play it again as you go through the same steps I do with Fusion 360 open on your computer. If you want to go over a part of the video again, I will have timestamps in the description and as the top comment. Let's get to it. The number one thing to check once you enter the design space is the units under document settings. This will save so much time and headache, especially if you are less experienced and unfamiliar with the workarounds like scaling. For navigating around, hold the middle mouse button to pan or Shift plus the middle mouse button to rotate. You can also use the navigation box in the corner. For newer CAD users, I recommend the following mantra: sketch feature, sketch feature, sketch feature. That means make a simple sketch of the largest dimension of your part, then make a feature from it, like an extrude or revolve. Then working from large to small, inside to outside, from bottom to top, you can make features from those sketches. Once you are more comfortable with that, start experimenting with the other tools and methods. First thing we want to start modeling is things we know, or real-world parts. So let's make a couple of bearings. If you have a bearing that you don't know the name of, like 608 or 925, just use the dimensions, which are inside diameter, outside diameter, and thickness. So this one that we're going to be building is going to be 5mm by 11mm by 4mm. And so you can save it as bearing 5 times 11 times 4 in your working project folder. When modeling, it's best practice to use the least amount of features possible. Not only to keep the timeline clean, but it's also a good thought experiment that gets you thinking about how to break down an object to model it more easily. So we can just keep it simple and do an extrude operation using the bearing's main dimensions. We start with a sketch, making 2 circles on the origin, one inside the other, using the inner and outer diameter dimensions. And you can press Tab after the first one to keep the circle operation selected. Otherwise, you'll have to select the circle again. Then we make sure the sketch is fully defined by giving it relations and turning the lines from blue to black, or white in this case if you're using a dark background. We see that since we selected the origin for both starting points, it gives a concentric relation automatically, showing by this little symbol right here. And then we finish the sketch. Now we will hit extrude. Select this face and extrude it by typing the amount or by pushing or pulling the arrow. And you want to get it to the bearing's thickness of 4mm. We will select the profile plane, symmetric, distance, whole length value, and the operation as a new body. You can use that as is if you're just trying to make a quick reference part in an assembly, but let's make it look a little more like a bearing. we are going to be selecting the face, hit Create Sketch, make 2 concentric circles with the inner diameter and outer diameter of the bearing shielding, and then extrude. Then we will select the profile plane, one side, and a distance of negative 0.1 millimeters, and have it as a cut operation. To have it on the other side, select the feature from the timeline on the bottom, go to Create, then Mirror, and select the mirroring plane as the front plane, and then OK. And now we can see that the operation was mirrored. Now we can make those little chamfers on the ID and OD. Select Chamfer under Modify. Select the faces to chamfer, make it 0.2 millimeters, and then hit OK. If we wanted to change the appearance, we change the material of the body to steel carbon, and right-click on the part and select Appearance. Select Apply to Faces, and then go down to Other, Rubber, then download and drag it onto the face, and do it for the other side too. Now that the bearing is complete, we will turn it into a component. So right-click on the bodies or group of bodies, select Create Component, and you're done. Now we will do this for each of the components in case you want to use them for other projects. Then you'll have the individual parts already modeled and available. Now let's use what we learned to make a 5 by 8 by 2.5 millimeter bearing using the same exact procedures. For a tie rod end, in the front plane, we will extrude a cylinder, and then an inscribed polygon, meaning the diameter is based on the corners instead of the flats. Then we'll align that to the extruded cylinder, and set the horizontal constraint to fully define it. Next is the rounded end. We're going to be making a sketch on the top plane. Grab these 2 edges and project them onto our sketch so we can reference them and turn them into construction lines. We can do that through the sketch palette on the right. Then we will put in a 3-point arc and use the constraints to make sure that the arc is tangent to the 2 lines, and close out the area to cut revolve, and make a center line through the origin of our axis of rotation. Without exiting our sketch, we could jump over to Solid and then Revolve, and it will automatically use the closed area and our center line to revolve a cut through the part. Now we make the captured ball section. We'll do the outer diameter vertically from the origin, and then place a construction line from the origin to the topmost edge, and then we'll set the measured values. Then we project the top line as solid, and make these lines on either side tangent to our outer diameter, and then trim these lower arcs. Make sure the sketch is fully defined after trimming, and extrude it as a join operation. Next sketch is on the right plane. We're going to be projecting these 2 lines and make a couple right triangles. Then extrude cut symmetrically through all. To get rid of these protruding corners, we will make a sketch on the top plane, project this line as a construction line, and make it a right triangle. If you really want to be fancy, you can use functions of other measurements for more parametric modeling. Put our center line through the origin and revolve cut through all. But since we are going to be doing the same operation for the next feature, we can go back into the sketch that we just came out of and put in the inner spherical cutout. Let's project this arc as a construction line and make a semicircle concentric to that. Make it slightly larger than our ball diameter, and if needed, we can go back into the revolve feature in the timeline and select this new geometry if it's not already selected. Now, don't forget the hole in the bottom. Then we can edit the appearance and turn this body into a component. Instead of making a new part file for the ball section, we can do it right in the same file, since they come together as a unit. So let's make a new body, and we'll do a semicircle concentric to this outer contour and have it revolved around the center line. Ensure that it's fully defined, and then hit revolve. Now we can go into one of our previous sketches and turn the last one visible. And we'll use this center point to make the next extruded symmetric join operation, and then the extruded cut operation through all. Let's change the material and turn it into a component. Now that we moved the ball out, select the spherical surfaces on the inside of one and outside of the other, and hit Make a Joint. Select Symbol for both, then have the alignments at 0, and go over to the motion type and select Ball. And now you can animate it to see it move around the pivot. Now here's a little challenge for you. I want you to pause the video and figure out how to make this tie rod. You don't need to model it. Just think of what the procedure would be to model it. What steps would you use? How many features did you use? Now let's go through and see if I did the same thing you would do. First, I'll make the 5mm box profile extrusion. And then the extruded shafts. I then chamfered the box profile corners and made a large chamfer for the transition area. After that, I cut the right-handed threads using the thread tool under Create, and then the left-handed threads on the other side. You can select Modeled, but if you have a lower powered PC, then you can leave it unselected to have mock threads on the surface. This is especially useful if you have large assemblies, as every facet of the threads can slow down your system. And here I'm just making a revolve cut to chamfer the ends. If you make the revolve cut before you do the threads will stop before the chamfer starts, and we don't want that. We want the chamfer to go through the threads, so that's what we're going to cut away. Now that we have modeled the off-the-shelf components, it's time to start our custom parts to integrate them. We're going to make a new file as our assembly to reference our other parts. So drag and drop the other parts into this build space, and we can do this for multiple copies of the same part. It's now time to start making relations and constraints between our parts, and this will hold them together in a way that allows us to build around. Let's drag and drop the 5x11x4 bearing, then right-click on the component and select Move Copy. Then make sure the Create Copy box is selected. Now we'll rotate and reposition the copy, and then we'll do that 2 more times. Now bring in the tie rod ends and the tie rods, and position them how you might assemble them in the real world. We will then select the concentric faces, or edges, and instead of making them rigid, we will make them revolute so that they can rotate around each other. I do this since linkages in real life don't have to be locked in alignment. They can be positioned rotationally how best they will move. We can further constrain their rotational motion later with more joints with other parts. We will also see later why it is important to select the components in the correct order so that the correct part revolves around the other. Now go ahead and mate up the rest of the components. Next, we're going to make a gap between our bearings so that we can have a 3D printed ledge separating the bearings. This will give us space to make the steering linkages. Let's start a new part with 2 concentric circles, one for the outer diameter and the other for the bearing outer diameter clearance. We will then model the separating edge by projecting our inner diameter and making the smaller concentric circle inside of that. Then we'll join extrude offset by the width of the bearing, which is 4 millimeters, and offset to the other face minus 4 millimeters for space for the other bearing. Let's save this part file and import the draft into our assembly. Then we'll give it a revolute joint around the bearings. Now we're going to go back into the draft part and give it linkage arms to help turn the rotary motion into linear motion. This is just an extrude on a couple of concentric circles with the inner being 2.5 millimeters, which is also a good size for screwing an M3 size fastener into a 3D printed part without having to tap holes. And then we will join it to the projected outer diameter line of the already extruded part. We can then go back into the assembly and see how it looks, making little changes where we see fit. Then we can clean up the look with a couple of chamfers and then turn it into a component and select the material properties. Then it's time to make the complementary steering arm, but with another protrusion 90 degrees offset, so we can turn linear motion in the y-axis to linear motion in the x-axis. Now we can clean it just like the other one with some chamfers and adjusting the material properties. Next, we'll update our assembly and start modeling the connecting linkage. This just has to be a bar with 4 holes. 2 inner at M3 fastener clearance, and 2 outer with our M3 threading diameter of 2.5 millimeters. Now we can import it into our assembly and start making the relations for joints between the parts. Here I am just making the base to mount everything to, kind of like a mock chassis plate. Due to me being mostly a SolidWorks main user, I made a few mistakes with the joints here. It's actually really important to pay attention to which part spins around the other. Otherwise, you'll have opposing forces trying to drive each other, and it really doesn't like that. It's actually best to start with the driving force. In this case, it's where the servo starts, and then work your way down, having the downstream parts doing the motion around the upstream parts. And if it actually doesn't do that, then just exit and then reselect the parts again in the correct order. I took a little time to reselect the parts in the way I just described, and this is the result. I can now control the linkages by turning just this one part. If you want, you can continue making more of the suspension components and continue the joints down the line. Let me know if you want me to continue this in the next video, or I can just move on to a different topic. The next thing I want to touch on is exporting for manufacturing. Did you notice that the linkage rod is a simple extruded 2D profile? This is on purpose, because now I can select the sketch used for the extrude and export it to a DXF. Then I can upload that into a CNC laser, CNC router, or even just send it off to a service like Send Cut Send and have it made out of 6061 aluminum. Making this video took a bit of time since I have a day job and a family, but it was a ton of fun. Let me know if you have any other topics that you'd like me to expand on. I just love 3D modeling and making parts out of my designs, and I look forward to sharing with you in the next one. Take care.